Hi everyone. Today I'm going to tell you about the technique to accurately estimate how existing optimizations or improvements in hardware capabilities affect the performance of DNN training. This is a joint work with my advisor at University of Toronto and my mentor at Microsoft Research. So first, a brief summary of my presentation. Our project is motivated by that DNN training is highly time-consuming, but the benefits of many proposed DNN optimizations are not easy to exploit for the following reasons. First, the efficacy of a DNN optimization varies when applied to different hardware-software deployments. And second, it is onerous for programmers to implement and debug the DNN optimizations. And this raises a demand for a solution that can quickly identify the effective optimization for any given deployment so that there's no need to try each optimization. For this purpose, we propose a system called Daydream, which allows users to quickly estimate the runtime improvements of common machine learning optimization based on their own deployments. Our system is based on the dependency graph analysis, and we identify three unique key requirements of using dependency graph analysis in the machine learning context. First, it needs to track dependencies at the abstraction of GPU kernels and properly construct a graph with thousands of nodes. Second, it needs to correlate the low-level kernel traces with the high-level layers of DNN models. And third, it should enable machine learning programmers to easily model a very diverse set of DNN optimizations. We extensively evaluated our Daydream system with five different optimizations over 5 DNN models, achieved low estimation error around only 8% on average. And we show that using Daydream, we can accurately estimate the distributed training runtime based on only a single GPU profile. So now let's look at the details. Over the past few years, machine learning researchers have proposed many DNN models. So the y-axis here in this figure shows the everyday amount of compute used to train these models. And this line suggests that the demand for DNN compute has been growing exponentially. This demand is not sustainable. So today we need not just hardware, but also other ways to improve the training performance. And therefore, researchers have been proposing many new advances in algorithms, optimizations, and hardware architectures every year. However, despite these advances, it's not easy for machine learning programmers to identify the efficacy of these proposals in their own deployments. So imagine a machine learning programmer who just developed a DNN model on his or her machine. And since the training could take like days or weeks, it's very common for him or her to ask questions like, why is my DNN training work running slow? What is the bottleneck? Or what if I implement certain optimization? How well will that improve the performance? And what if I get the latest GPUs and my compute is 2x faster? Or how will my workload scale with the number of GPUs? Or what if I upgrade to a faster network? How will that improve the training throughput? Answering these questions is not easy because you often have to spend time on implementing and debugging certain optimizations, or you need to pay for some extra compute power. But luckily, exploring what-if questions is not an entirely new problem. The system researchers have been using this dependency graph analysis approach to answer performance-related what-if questions in some non-machine learning contexts, like big data processing systems. And on the other hand, dependency graph structures are also common in the machine learning context. So for example, many DNN models are specified using dependency graphs, and mainstream machine learning frameworks also perform the computation based on the dependency graph structures. So the similarities between the graph structures suggest that we can use the idea of dependency graph analysis for our system. However, we identified several unique challenges when using this approach in the machine learning context, and there are also opportunities. The first challenge is that we need to build a graph with nodes at the abstraction of GPU kernels. Here's an example of showing like what the low-level execution timeline might look like. Each box here corresponds to one GPU kernel or a CUDA API, and we'll have a corresponding node in the dependency graph. And there are usually like thousands of such boxes in just one training iteration, and meaning that the graph will be huge. And the dependencies need to be tracked across all these traces at different threads and strings. And the second challenge is that some optimizations will operate at the kernel level granularity, yet still requiring the knowledge of DNN layers. The machine learning people are very familiar with the DNN model graph. However, Daydream's dependency graph is at kernel level. So say a programmer wants to know like what if he or she can speed up the convolutional layers by 2x. It's hard to model this because there's no profiler that can tell us which kernels belongs to the convolutional layers. Hence, the system should find a way to correlate these two different abstractions. And the third challenge is that there are various DNN optimizations. So suppose we train a DNN using multiple machines with multiple GPUs. A DNN optimization may try to optimize the algorithms, the CPU or GPU, or the inter or an interconnect. And with the same optimization goal, there are often multiple techniques to do that. This diversity of DNN optimizations raises the challenge that systems should allow users to easily model the common potential optimizations. So before we dive into how Daydream addresses this challenge, let's first go through Daydream's workflow. So the system takes two inputs. The first one is a DNN training implementation X, and the second one is an optimization Y. And the outputs the estimation of runtime when applying Y to X. So given a DNN training implementation, Daydream will first run a profiler on top of it, collecting profiling data and generate both kernel level and layer level traces. And then Daydream will combine these traces, generating Daydream's dependency graph. The users will use Daydream's transformation primitives to depict the given optimization. And these primitives will alter the dependency graph. And finally, the Daydream will simulate the post-optimization graph to output the final estimation. And now let's look at each challenge in details. So the first challenge is that the Daydream has to check dependencies across thousands of low-level traces and across different hardware. Here are two figures showing the kernel-level traces of training a ResNet 50 and BERT large models. So there are thousands of GPU kernels and CUDA APIs invoked in just one iteration. Hence, the Daydream needs to construct a graph that is potentially extremely complicated. But we notice that the GPU kernels in the DNN training workload are usually highly serialized. Such serialization property is due to that the GPU kernels are mostly compute intensive and hence are carefully crafted to fully utilize the GPU resources. And this leaves very limited space for concurrent kernels. And this observation actually greatly simplifies our construction of the dependency graph. So based on this observation, we identify 6 types of dependencies that we need to track so that Daydream can accurately replay the execution. So first, 2 consecutive CUDA APIs on the same CPU thread will have a dependency between them. And second, similarly, 2 consecutive GPU kernels or CUDA memory copies on the same GPU string will have a dependency between them. And third, each GPU kernel or a CUDA memory copy is invoked by a corresponding CUDA API. And therefore, there should be a dependency from the launching API to its GPU kernels. And fourth, when calling a synchronization call on the CPU thread, the thread will wait for GPU kernels to complete. And this creates a dependency from GPU kernels to a CPU call. And then we have dependencies from CPU tasks to communication calls because we aim to estimate distributed training runtime. When estimating the distributed runtime, we first collapse the CPU calls and GPU kernels into layer-wise forward and backward tasks. And then we add dependencies between the compute and communication tasks. If we model a parameter server architecture, we need to add push or pull operations. And if it is a decentralized architecture, we need to add or reduce operations. And finally, for the completeness, we have CPU to CPU dependencies representing the thread spawn, join, the lock, etc. Once we properly construct all the 60 types of dependencies, Daydream is able to accurately replay and estimate the runtime. And the second challenge we need to address is the correlation between the low-level traces and DNN layers. This is required because DNN optimizations might operate at kernel level, but requires the knowledge of DNN topologies at the same time. So for example, one way to improve the training of a convolutional network is to fuse a convolutional layer with the activation layer. Unfortunately, the kernel level traces has no domain knowledge. Therefore, we have no idea which traces belongs to which layer. And naively, people solve this problem by adding synchronizations. So suppose we have a timeline that looks like this. Then when inserting a synchronization, we can measure the time of GPU kernels on the CPU thread, and then compare the timestamps of the time span of the with the time span of the GPU kernels. This approach is simple, but as we can see, it creates an additional dependencies. And this is not good because it alters the dependency graph. Daydream addressed this challenge using a synchronization free mapping. So let's use this timeline for example. Suppose that K0 and K1 belongs to the layer 0. We first time the start and stop timestamps of L0, layer 0, and then get all the CPU tags that belongs to the L0. And then using the dependency information, we can find the GPU kernels that launched by L0 and map them to L0 as well. This approach introduces little overhead because we only instrument per layer timestamps to the frameworks. And there's no alteration to the dependency graph because we didn't inject any synchronizations, so that the profiling trace we collected is actually accurate. The third challenge is that there are just various DNN optimizations targeting different performance bottlenecks in different ways. So some optimizations, for example, aiming at improving the hardware utilization in a single worker environment, while some others try to reduce the communication overhead in distributed training. These optimizations often use like different strategies to achieve their goals. So for example, to improve hardware utilization, one can either reduce the precision or fuse the kernels or layers. And there are just multiple techniques that implement each of these strategies. Similarly, there are many optimization techniques that try to either reduce communication overloads or improve the communication computation overlap. In our papers, we show that using Daydream, we can easily model the ones that are highlighted in bold italic and accurately estimate the efficacy of the optimizations shown in green. To address the challenge of DNN optimization diversity, we propose a set of simple transformation primitives. Based on our previous design, we found that the most DNN optimizations can be described as a combination of very simple graph transformation primitives. So the first one is the selection primitive. So a DNN optimization could affect a lot of nodes in the dependency graph. And user can use this primitive to get all the nodes of interest for the further process. So for example, when we estimate the performance of reducing precision, user can use find the effective test by selecting all the GPU kernels. Or if a technique improves the convolutional layers, you can select all the GPU kernels that belongs to the convolutional layers. And the second one is just shrinking a scaling task duration. So say we shrink the duration of all convolutional layers by 2x, the timeline will look like this. We then have the primitives allowing users to manipulate the dependency graph topology by inserting or removing nodes. So suppose that we have a simple timeline that looks like this. And inserting a CPU task between them is just like inserting a node to a linked list. And a removal is just a reverse of the insertion. And when inserting a GPU task, it's a bit different because a GPU kernel has a corresponding CUDA API to launch it on CPU side. So when inserting a GPU task, we need to also insert a CPU task at the right position, representing the CUDA launch API. And again, remove is just the reverse of an insertion. And the last primitives allows users to reschedule the execution of the graph's tasks to achieve better overlap. So for example, for a timeline shown below, one can switch the order of gradient exchange of L1 and L0, leading to a timeline that looks like this. Since both timelines are based on the same dependency graph, to achieve this rescheduling, users will need to override the schedule function. The schedule function returns one task from a queue of tasks that are ready to execute, and this function is evoked by the simulation process. Users can override it and implement any custom scheduling policy. So far, we have introduced the Daydream's transformation primitives, which might look very simple, but actually very powerful. So we show one example of using Daydream to model the optimization of automatic mixed precision. So the modeling process takes two inputs from the Daydream profiler. One is the low-level traces collected by using CUPTI, and the other is per layer timestamps collected by instrumenting the machine learning frameworks. We then construct the dependency graph, a Daydream's dependency graph based on the low-level traces, and map the low-level traces to DNN layers. And then we can select all the GPU tasks from the graph and check how AMP affect the duration of each GPU kernel. So we shrink a GPU kernel by 3x, the duration of GPU kernel by 3x, if we expect this kernel to use tensor core, and 2x otherwise if it uses half precision cores. And finally, we simulate the altered graph for a runtime prediction. The code is written in Python, showing our prototype implementation of Daydream user programs. And this is a very simple example. In the paper, we will show 9 other examples, and each of them takes only around 20 lines of code. So for the last part of my presentation, I will show the evaluation of Daydream's estimation accuracy. So we evaluate Daydream using 5 DNN training workloads. We use 20 TTI and P4000 GPUs, and we add in Daydream instrumentation to PyTorch, MXNet, and Caffe. We evaluate 5 DNN optimizations. 3 of them aim at improving hardware utilization, including AMP, fused atom, and reconstructing batch norm. So the fused atom optimizer is from a VDS open source package, which fuses all kernels in the atom optimizer. Reconstructing batch norm is an approach to overlap GPU compute latency with GPU memory latency through kernel fission and fusion. And we also evaluate this data parallel distributed training and priority-based parameter propagation, also called P3, which is a technique to improve the computation and communication overlap. So for each optimization, and the DNN training workload, we evaluate the following. The first, a baseline showing that the iteration time of just running the workload. And second is the ground truth showing the iteration time after applying the optimization to the workload. And third is the prediction, so showing the Daydream's estimation of the optimization. And we first show the evaluation of the three optimization techniques, which are automatic, mixed precision, fused add-on optimizer, and reconstructing batch model. So the y-axis here shows the different combination of optimizations and the training workloads. And the y-axis shows the iteration time. So when using ANP on BERT-based model, we achieve 1.54x speed up. And using Daydream, we predict this speed up to be 1.36x. The difference is only 5.5%. And we did the same analysis when using ANP on other three models and achieve prediction error around 50% at maximum. We also evaluated fused add-on and reconstructing batch norm optimizations, achieving very low estimation error. So in general, Daydream achieves 8% estimation error on average and 15 maximum. We then show Daydream's prediction of distributed training runtime. So the runtime is running on a single machine with a single GPU, and we vary the system configurations in multiple dimensions, including the number of machines and the number of GPUs per machine, and the interconnect bandwidth. So the green bars here shows the measured ground truth runtime of the BERT large model, and the red bars shows the runtime prediction. And the estimation error, as we can see from the y-axis on the right-hand side, is generally less than 10%, and showing that Daydream can accurately estimate the distributed performance for various system configurations. We also evaluate three other DNN training workloads, and as you can see, the estimation errors are still generally less than 10%, and showing that Daydream can accurately estimate the distributed training performance for a variety of DNN models. And finally, we show the evaluation of P3. We use 4 machines and one P4000 GPU on each machine to replay the evaluation of P3 on the paper. So here's the figure showing how Daydream's estimation of using P3 on ResNet 50, and we vary the x-axis is the network bandwidth. This is the baseline, and the improvement of using P3 is actually subtle. And the prediction curve almost overlaps with the ground truth curve. It's the same for GPU VGG19, that the prediction curve is very close to the ground truth curve. But the improvement of using P3 is significant. So this suggests that using Daydream, we can successfully estimate whether P3 will provide significant or subtle improvements. So to conclude my presentation, our project is motivated by that the benefits of DNN optimizations are not easy to exploit. And based on the idea of using dependency graph analysis, we built a system called Daydream, allowing users to quickly estimate the performance of various DNN optimizations. And Daydream's design features 3 key ideas. First, it's the tracking dependency at the kernel level. Second is the synchronization-free trace-to-layer mapping. And it also proposed a set of simple graph transformation primitives. In our evaluation, we show that Daydream can achieve low estimation error of 8% on average, and we are able to model a wide range of optimizations with only 20 lines of code around each. So here's my presentation, and thank you, everyone. If you have any questions, you can send me emails.